Good day, bright physics students. So for today's video lesson, we will be discussing Introduction to Dynamics and Statics, or more specifically, our focus is on lesson number 1, which talks about Newton's laws of motion. But just like what we did with our previous video lessons, before we deal with the main topic, let's try to identify or discuss first some fundamental concepts in order to understand better what we'll be discussing for this video. So without further ado, let's try to identify first the word dynamics. So dynamics, according to our description written on the slide, is a branch of classical mechanics concerned with the study of forces and their effects on motion. Aside from that, it also deals with the motion of material objects in relation to the physical factors that affect them. Like for instance, how do forces affect the motion of or the changes in motion of our object of interest? Now, before we deal with dynamics, in our previous video lesson, we strive to understand the word kinematics, and we knew that kinematics deals with the course of motion of our object of interest, which means that we wanted to identify whether the object's velocity or acceleration changes over time along a straight path, or maybe if that object travels along a curved path or perhaps a circular path. So that's the main focus of kinematics. However, for dynamics, we're striving now to identify what causes the changes in motion of our object of interest. Right? Just like what the word force, or what the physical quantity force is actually doing. So, a little bit of a disclaimer: although forces do change, or is actually a cause of changes in motion of our object, it doesn't. Forces isn't the only physical factor that could do that. Torques could possibly do that as well, or maybe momentum. But again, for this specific video, we'll be dealing with forces alone. So yeah, before anything else, we wanted to identify what are the different types of forces according to classical mechanics. So according to classical mechanics, there are two types of forces. One is a contact force and the other is a field force. So for contact forces, it is characterized by direct interaction with another body. So let's say, for example, you are currently taking down notes from this video. So your body interacts, or is apparently in a direct interaction with the body of the pen. So that is a great example of a contact force. However, for field forces, the word used in here is influence. So although there are not any direct interaction happening between two different objects or two different bodies, field forces happens due to non-contact influence with another body. So what is a great example of field forces? We do know that the planets, we do know that the planets is revolving around the sun along its own orbit, and these planets do not move away from their own orbits. So we can actually deduce that from these basic ideas that there is something that holds those planets, for these planets to not move away from their orbits, and these are the field forces. So in order to understand better what are the contact forces and field forces, let us try to identify their subtypes. So let's start with contact forces. So here are the subtypes of contact forces. We have 5. So for this first image that we have right here, we already have 2. So this red vector line with the symbol F sub A is what we call as the applied force. So applied force happens when a body exerts a force upon another body. So in this example, we have here the stickman pushing the box. So basically, the stickman applied a force towards the box so that it could move, right? So that is the basic idea of applied forces. So you could push an object or you could pull an object of interest, and that is a result of a force that you actually applied. So the symbol that we use for applied force would be F sub A, and that is the direction of the applied force in our example. Now, this blue vector line is opposite of the direction of the motion of the object. So if the motion of the object is towards the right because the stickman pushes the box to the right, this force is opposing that motion. And this blue vector line is what we call now as the friction force. And the symbol for friction force is small letter F. So according to our definition, it is an opposing force exerted by a surface as an object moves across it. So friction forces are already present when there is a contact between two different surfaces. So let's say for instance, we have here the box and the surface of the ground. So these two surfaces interacts with one another. Therefore, there is already a friction force happening between them. And it's opposite of the direction of motion. So since the box is moving to the right, the friction force is moving to the left, or is directed towards the left side. Another thing, the stickman right here is also in direct interaction with the box. So his hand is exerting a friction force also towards the box. Alright, so as long as there is an interaction between two different objects, there is already a force between them. Next, how about this second picture? The second picture happens to show us that there is a force that is happening in the strings or in the rope. So this force is what we call as the tension force. So it is transmitted through ropes, wires, cables, strings, and such when it is pulled by another force. So tension force, the symbol that we have for that would be big letter T with an arrowhead. So it is happening only in anything that is most likely to look like a string, right? And it happens on both sides of the string. So if the string is being pulled on the other side, it must be even being pulled on the other side. So yeah, there would be tension inside that object. Next, so the last two examples of or subtypes of contact forces would be this one or these two. So the first one is already written on the picture, so it's what we call now as the normal force. So according to our definition, normal force is exerted on an object that is in contact with a stable surface in order to support the object. It is always perpendicular to the surface. So before we understand what happens with the normal force, let's try to identify first where does the term normal came from. So if we are this came from actually in our idea of mathematics in mathematics. So let's say that we have here a point in a graph, and then this is our graph. Now this line, the line that touches the graph once and it's in its whole lifetime per se, that point or that line is actually the tangent line. So the normal line is a line that extends from the point of interest and is perpendicular to the tangent line, and this is what we call now as the normal line. Now, since all of the particles or object of interests in physics is treated as a particle, that would be the point in the graph. Yeah, that's similar to the point in the graph. Now, these surfaces where the object of interest is located, let's say for instance in our example right here, we have here the table. So the surface or the table surface would be the tangent line. And to identify the normal force is perpendicular to the surface. Yeah, you should always remember that the normal force or the direction of the normal force is always perpendicular to the surface. So that's it. Now, what what is really the function of the normal force? The normal force is the one that's actually supporting the object of interest so that it could be stable above a certain surface. So let's say for instance we have here the box, and it is supported, or the weight of the box is actually supported by the surface of the table. So the table exerts an upward force towards the box, and that's what we call now as the normal force. And lastly, we have here this one. This is what we call now as the spring force. Spring force, or F sub S. By the way, I haven't mentioned here the symbol that we use for normal force. We don't actually use big letter N because, or we wanted to avoid any confusion with the unit that we use for forces, because the unit for forces is in newtons, and the symbol for newton is big letter N. So in order to avoid confusion, we can use small letter n for normal force, or F sub n. Any of the two would be acceptable. Alright, let's get back to spring forces. So spring forces, the symbol that we use for that is F sub S, and this is sometimes called as the restoring force. So why was it called the restoring force? Because the natural inclination for all springs is that when they are stretched or compressed, they tend to find, or they tend to seek their normal state. That's why it is also called the restoring force, because this spring force would only be present when they are compressed or stretched to find or to locate the spring's normal state again. Alright, so those are the 5 subtypes of contact forces. So 1 again is applied force, number 2 would be friction force, number 3 is tension force, number 4 is normal force, and number 5 would be spring force. Alright, so now that we're done with contact forces, let's proceed with field forces. So the first one is right here. So it is exemplified by an apple moving down because of a certain force, and that force is what we call now as the gravitational force. So the biggest connotation that we have when dealing with gravitational force is that it is always pointed downwards. But the thing is, that statement would only be correct when we are located on a certain rigid object in the universe. So let's say a planet or a satellite. Therefore, there will be a certain gravitational force that is actually pulling you towards the center of that planet. So apparently, the motion of the gravitational force is towards the south, or is downward, because it tends to pull everything towards its center. But what if you are located outside the safety of the planet? So you're located on the vacuum of space. So gravitational force would be present when there is a body, or there are bodies that have masses. So F sub g is the symbol that we use for gravitational force. So again, let me reiterate that. So it is an attractive force, and this will be present when there is a mass. There is also a mass that is present. That's why there is a gravitational force that is acting for the sun, and between the sun and the planets. Alright, there is no direct interaction between them, but because they have masses, there is a gravitational force existing between them. Alright, now how about these two right here, or these two images or GIFs below? So these two are an example of electromagnetic force. So if gravitational force is an attractive force, electromagnetic force is both an attractive and a repulsive force. So again, this is an attractive and repulsive force. And why do we combine the two ideas in physics, which is electricity and magnetism. Because as you may see in these diagrams or simulations, um, both quantities, both physical quantities, actually exhibits the same or almost the same characteristics. That's why you can actually summarize them into one major idea in physics, and that's electromagnetism. So electromagnetic force is a causes an attraction or repulsion between two charges. So for electric forces, we have here two different charges with two different signs. So one is a positive charge and a negative charge. For magnetic forces, we have here two different sides. One is a north pole and the other is a south pole. So for the force of attraction to exist, you need two different signs and two different poles. And for the force of repulsion to exist, it must be of the same sign. Alright, so let's say for instance, for attractive forces to happen, a positive sign and a negative sign of charges shall exist, and for repulsion to happen, both positive charges could do that, or both negative charges could also do that. Alright, so now, aside from these two field forces, there are also two other field forces, and the first one would be the strong nuclear force. The strong nuclear force is the reason that elementary particles are binded all together. So for the subatomic particles to actually exist, like the proton and the neutron, these elementary particles shall be binded all together, and the reason the force that actually does that would be the strong nuclear force. And this one below, so simulation shows that a proton is bombarding a nuclei atom, a heavy nuclei atom, and then it splits the atom into half, and then by doing so, it also releases a form of energy. So these is a result of having weak nuclear force in our own universe. So weak nuclear force is responsible for the radioactive decay or radioactivity. So now, these four field forces, are actually kind of the terms that you have already stumbled upon when you are discussing or you are taking earth sciences classes or earth and life sciences classes. So these four are what we now call as the four fundamental forces. So the modern science accepts the idea that these four fundamental forces are the actual forces that shaped the whole universe as it is right now. So the gravitational force, the electromagnetic force, the strong and the weak nuclear interaction are the only forces that is responsible for the creation of the universe. So if we try to look at it, or if we try to look at the whole universe atomically, there is no actual contact force that is happening all around us, because inside the atom, between the electron and the nuclei, there is already a space between them. Inside the nuclei, the protons and the neutrons also has spaces between them. Between those subatomic particles, the elementary particles also has some spaces between them, and inside them, the quarks also does have spaces between them. So in actuality, or in conclusion, there is no actual contact forces, but rather all of the things that we are experiencing right now is an effect of fundamental forces interacting with one another, or mainly that's because of the charges that we have on our atoms, because the electron is exhibiting negative charges, and the proton is exhibiting positive charges. So that's because of the interaction of these charges that we can apparently interact with other objects or with other matter. Yeah, that's how science actually works. Now, since we're already done with identifying the subtypes and the types of forces according to classical mechanics and in modern science, so now let's try to identify what do forces actually do. So in junior high school, we're accustomed to the idea that forces is defined as a push or a pull, which means that the basic connotation that you can actually get from that is that forces do cause motion, or forces causes motion, just like what this woman would actually do. So the woman kicked the ball, and then in effect the ball bounces. So yeah, forces do cause motion. Aside from that, this could be also a great example. So the man tosses the ball or throw the ball towards the wall. So he exerts a force towards the ball. Therefore, the ball is in motion towards the wall. Alright. So yeah, forces do cause motion. But how about these two pictures? So the cat in here is sitting and is the back is pushing, I guess, on the wall behind the cat, and this person, so this man is pushing the pole, and to no avail, the pole isn't moving. So does that mean that the cat and the person pushing the pole is not actually exerting force towards towards the other body? Right, the answer would be no. They still do, they still exert force. But what can we infer about the situation? This situation reminds us that forces sometimes do not cause motion. Which means that in these systems, the net force, alright, the net force is equal to 0. So just like this one, the man pushing the pole, but to no avail, the pole isn't actually moving. So the net force, so by the way, the symbol that we use for the net force is summation of F. So this is the net force. The net force is actually the total force inside the system. So the net force is equal to 0, which means again that the system is in equilibrium. Alright. So if the system is still is in equilibrium, therefore it is not under the branch of dynamics, but rather this is now under the branch of statics. So statics is the study of forces without motion. So it deals with the analysis of loads, force and torque or moment acting on physical systems that do not experience an acceleration. So just like what we mentioned in our previous video lessons, when dealing with kinematics, you're only trying to understand the course of motion. When dealing with dynamics, you are trying to understand the causes of the changes in motion, like per se the effect of forces in the changes of motion of a certain object, while statics is focused on the objects that are in equilibrium. So you need to understand the distribution of forces or the torque or the moments in that specific system, why that system is not moving or is stable or is in equilibrium. Alright, and that is the focus of statics. So right now, since we're done with the identification of dynamics and statics and all of these subtypes and types of forces, let's deal with what is force actually. So what is a force? So right, it is a push or a pull. But how can we identify whether a force is actually or is already present inside the system? So we can do that if we can actually know that a force is already present in a system if there is an interaction between two different objects. So yeah, there is a push or a pull, but how do we know that the force is now present in the system? So if there is an object, if there is an object to object or a body to body interaction, then there is already a force. That's why it's characterized by push or pull. But when that interaction ceases and when it's eliminated, or there is no interaction happening inside the system, then the two objects could no longer experience the force between them. Alright? And what is the unit that we use for force? It was already mentioned earlier. The unit that we use would be Newton. Alright? And Newton is a derived unit. As you can remember, a derived unit is a combination of fundamental units. So these are the fundamental units that we have for Newton. That's kilogram meter per second squared. Alright. So since now that we're done with forces, the concept of force, let's now deal with the Newton's laws of motion. And what better way to start it is by doing or by understanding the first law of motion, which is more popularly known as the law of inertia. So Newton's first law, or the law of inertia, uses the idea of the word inertia. And inertia, according to our description right here, is defined as the tendency of an object to resist any attempt to change in its velocity, or to change its velocity. So, our main assumption right here is that no forces should act on the object of interest. So let's write it in here. The net force shall be equal to 0. Now, let's say for instance we have here a hockey puck. And since our assumption is that no forces shall act on the object of interest, okay, this hockey puck is already moving at a certain velocity. So this is the velocity of the puck. Now, the puck is located on an ice range. And the ice range, since again, no forces should act on the object, and we knew that friction force is a type of a force. So we will assume that the surface is frictionless. Alright. Now, if the hockey puck is moving at a certain velocity at that point, so if it's now located at this point, okay, if it's now located at this point, what would be its velocity? So many would say that the velocity of the hockey puck at this point would be the same as the velocity that the hockey puck has right here on this point. So yeah, that would be correct. So the velocity, or the initial velocity of the puck, is also similar with the final velocity of the puck. So that's Vi, or the initial velocity, would be equal to the final velocity. And since both of the velocities are equal, we can actually deduce that the acceleration, since acceleration is defined as the rate of the change in velocity, and there is no changes happening in the velocity of the particle, so acceleration would be equal to 0. So yeah, inertia is the tendency of an object to resist any attempt to change its velocity. So the greater the mass of a certain object, the greater the inertia of that specific object. Alright? Now, next. So how will we define, or how will we state the Newton's first law of motion? So according to Newton's first law, in the absence of external forces, alright, in the absence of external forces, and when viewed from an inertial reference frame, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity, that is, with a constant speed in a straight line. Now, we all knew the definition for the definition for inertia is already stated on this statement. So in the absence of external forces, so the main assumption that we had before is already used in this in this statement. And then since inertia is actually working for these objects under the Newton's first law, an object at rest will remain at rest, and an object in motion will stay in motion with a constant velocity. But how do we view it from an inertial reference frame? So we must understand first what is a reference frame and what are the types of reference frames. So, what are the types of reference frames? So we have two different types. One is inertial frame of reference and the other is a non-inertial frame of reference. So the only difference would be that the magnitude of acceleration for inertial frame is equal to 0 and for non-inertial frame is not equal to 0. So therefore, for an inertial frame of reference, the velocity would be constant both in direction and in magnitude. Alright, so both in direction and magnitude. However, since for non-inertial frame of reference, acceleration is not equal to 0, therefore the velocity is changing. Changing in what? Changing in direction or changing in magnitude. So, reference frames, how do we consider reference frames? We consider the reference frame of the object of interest. Alright, so let me just write it in here. The object of interest. And of course, the observer. So, the object of interest reference frame, if we try to consider the first actual example that we have a while ago, which is about the hockey puck, since the velocity of the hockey puck doesn't actually change both in magnitude and in direction, so the acceleration is equal to 0. Therefore, the hockey puck is in the inertial frame of reference. However, us as observers, what is our reference frame? So if you are right now sitting in the comforts of your home, then maybe your reference frame is inertial. So majority of you would say inertial, but let us consider this. So since we are located, the Philippines is located near the equator, so if we are near the equator and the earth is rotating on its axis, so we can assume that the path that we are actually moving relative to the earth is a circular path. And we knew that the velocity or the speed of the rotation of the earth isn't actually changing, and you're right now sitting on your chair, so your velocity is the magnitude of your velocity isn't actually changing at all, but the direction is changing as the earth rotates on its axis. Therefore, there is an acceleration happening as a consequence for that motion, and that acceleration is pointed towards the center of the planet. So that acceleration towards the center of the planet is what we call now as the centripetal acceleration, and this centripetal acceleration is more popularly known as the acceleration due to gravity, because they have the same function. The acceleration due to gravity of the earth is also the acceleration or the rate at which the earth is also pulling us towards its center. That's why they are equal, and this is equal to negative 9.8 meters per second squared. Now, so technically we are in a non-inertial frame of reference, but however, since the acceleration due to gravity of the earth is so small, if we try to include that in our calculations in identifying the net force that a body or an object of interest is actually experiencing, with us considering the inertial or the reference frame of the observer, the effect of this acceleration towards the center of the planet is extremely small and could be negligible. So we can actually assume or safely assume that even though we are in a non-inertial frame of reference, to avoid any confusion, we can assume that we are in an inertial frame of reference. Alright? So I hope that is clear. So now let's proceed with Newton's second law of motion, which is the law of acceleration. So the law of acceleration states that F is equal to ma, right? And F right there is the force, m is the mass, and a is obviously the acceleration. So why do we need to identify the mass of the object, and how can it affect the motion of the object? So yeah, let's focus first on masses. So which ball requires more effort to throw it? So obviously the answer would be the bowling ball. Now, in chemistry, we define mass as the amount of matter stored inside a system. Alright, so this is in chemistry, in the context of chemistry. However, since we are in physics, how can we use our answer that the bowling ball requires more effort to throw it rather than the basketball? So what is the effect of mass in the motion of the object? So, since the bowling ball is definitely having more mass than the basketball, it would be hard for us to throw the bowling ball rather than the basketball. Therefore, mass in physics is a property of an object that specifies how much resistance an object exhibits to changes in its velocity. So it's quite obvious that a more massive object would be hard to it would be hard for us to change the motion of that object. So if it's not moving and you wanted to try to make it move, it would require more effort to do that rather than if the object is less in mass. And if that object or a more massive object is actually moving, it would be hard for us to change its velocity or to stop it per se. Alright, so yeah, that's the concept of mass in physics. It's a property that specifies how much resistance an object exhibits to changes in its velocity. Alright, so now, since we already have the idea of masses, how can we differentiate that to weight? So in metric system, and in trying to get your BMI, you are required to get your weight using a weighing scale. So the term used is weight rather than mass. So what is the actual difference between these two terms? Alright, so according to our definition right here, mass is a physical property which opposes the motion of the object. And mass is a constant property. So which means that if your mass on Earth is 55 kilograms, then your mass on the planet Mars or on the moon is still 55 kilograms. However, your weight is dependent on the acceleration due to gravity of the location of that of the particle. So according to our definition, again, weight is a force. So, by the way, weight's symbol is W, big letter W with an arrowhead. Since weight is a force, so where or what subtype of forces can we actually consider the weight as a similar quantity? Since it depends in the acceleration due to gravity, then therefore it is safe to assume that weight is similar to the idea of the force due to gravity. And since, according to what I've mentioned earlier, second law of motion's famous equation is F is equal to ma. So since F is equal to ma, we can actually use that. So F sub g is equal to ma sub g, or weight is now equal to the mass, or the product of the mass and the acceleration due to gravity. And we knew that the acceleration due to gravity is equal to negative 9.8 meters per second squared. So, our weight on Earth, if your mass is again 55 kilograms and the acceleration due to gravity on Earth is 9.8 meters per second squared, then therefore your weight on Earth, again, let's write in here 55 kilograms times negative 9.8 meters per second squared, then your weight is equal to negative 539 newtons, since the unit newtons is the one that we use for forces. So what can we deduce from these ideas? So weight is actually a force, and it is a result of the interaction of your mass with the acceleration due to gravity of a certain rigid object. Now, what happens to your weight when you, let's say you wanted to migrate on the on our natural satellite, so on the moon. So on the moon, the acceleration due to gravity is equal to negative 1.62 meters per second squared, approximately. So what happens to your mass? What happens to your mass when you wanted to migrate on the moon? It remains the same because it's constant. However, your weight does change. So your weight on the moon would be, so your weight on the moon is 55 kilograms, that's your mass, times negative 1.62 meters per second squared. So your weight on the moon will be equal to negative 89.1 newtons. So what can we notice? So the weight is reduced, your weight is reduced, or the particle's weight is reduced when the particle is located on a smaller rigid object. So obviously the moon is smaller than the size of the Earth. That's why the weight of the object there is smaller than the weight of the object on Earth. Right? So what actually do we measure on the weighing scales on Earth? So the weighing scales on Earth is actually designed according to our acceleration due to gravity. So even though the ones that we see in the weighing scale is in kilograms, that would be technically correct as well, because the weighing scales are in accordance to our acceleration due to gravity. So it has not much of a difference. Alright, so again, our conclusion is that if our mass would be the same for all of the places in the universe, but our weight would be different depending on our location in the universe. Alright, so what is Newton's second law of motion? So Newton's second law of motion is stated right here, and according to our statement, that's when viewed from an inertial frame of reference. So this is the frame of reference of the observer. Alright, so this is the frame of reference of the observer. So according to the observer, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So the summary is this. Mathematically, acceleration is directly proportional to the net force and inversely proportional to the mass. So to eliminate the direct proportionality sign, we introduce a constant which is equal to 1. So acceleration would be equal to the net force divided by the mass. So what happens to acceleration if we wanted to double the net force? The acceleration becomes doubled as well because it's directly proportional. What happens to acceleration of the particle when the mass is doubled? So if the mass is doubled, then the acceleration would be halved. And what happens to the acceleration when the mass is halved? So the acceleration would be doubled because it's inversely proportional to mass. Alright? So to make this formula linear, so this will become net force is equal to the mass of the particle multiplied by the acceleration of the system. Alright, so this is the general formula or the summary of the Newton's second law of motion. Alright, so let's try to apply it to certain examples. So let's say that this car is moving at a constant velocity. So when this car is located at this point now, alright, so let's just draw it in here. So when this car is located at this point now, the velocity of the car would still be the same as its original velocity. So again, what will happen to the acceleration? The acceleration of the car would be equal to 0. And since according to our formula, the net force is equal to mass times acceleration, any number multiplied to 0 will be equal to 0. So the net force of the system will also be equal to 0. So again, what is the definition for the net force? The net force is simply the total force of the system or experienced by the particle. So if our object of interest for this specific example will be the car, so let's draw a particle model for the car. So let's say that this particle symbolizes the whole mass of the car. Now, since the car is moving along, let's assume, alright, that the car is moving on a flat surface. So the car's weight is being pulled, or the car's mass rather, is being pulled constantly downwards by a certain force. And that force is the force due to gravity, which again is equal to the weight of the car. Now, since the car is located on the surface of the road is exerting an equal force upward to support the weight of the car, and that's what we call now as the normal force. Alright, since the car's wheels are interacting with the surface of the road, these interaction produces what we now call as the friction force. And the friction force is opposing the motion of the car and is directed towards the opposite direction. So this will be the direction of the friction force. Alright. And how about the applied force? The applied force is, of course, towards the motion of the object. So the driver steps on the gas pedal, and that force exerted by the driver would cause the car to move forwards. So right now, this would be the applied force of the driver on the car. Now, is this applied force equal to the net force? I mean, is this applied force equal to the friction force? In magnitude, they are equal, of course, because according to our scenario, the net force inside the system would be equal to 0. And in order to do that, in order to accomplish that, all the forces inside the system should be equal to 0. And since the normal force is opposite in direction of the weight of the car, so these two are equal and opposite in direction, therefore they cancel each other out. So the applied force magnitude should be equal to the magnitude of the friction force, but they're opposite in direction. That's why the magnitude of the net force will be equal to 0. Now, this is a little bit confusing because we knew that the car is moving at a constant velocity. That's correct. The car is moving, but at a constant velocity. Because it's moving at a constant velocity, all the forces inside the system are in a state of equilibrium. That's why the net force is equal to 0. However, if the driver inside the car wanted to accelerate the car, so definitely if the car is accelerating, the velocity will change. So if a car is moving at a changing velocity, therefore the acceleration will not be equal to 0, and then therefore the net force will also be not equal to 0. And what happens to applied force? So in this case, the applied force would be increasing in magnitude. Alright, that's why the net force, or the distribution of forces inside the system, is not equal to 0. Alright, so what we have done in here is what we call as the force diagram, or in other terms, it is called as the free body diagram, or FBD. FBD again is sometimes called as the force diagram, and this diagram is used by most physicists and engineers to analyze and understand the distribution of forces inside the system. Not just forces, again, this FBDs could also be used to identify the distribution of torques or moments. So this is a very simple diagram for, or example for a free body diagram. So a little meme that I have managed to get from a certain social media would be this one. So what others see and what we will see if, once you have already done in trying to get an AP class, an AP physics class, or a general physics class. Alright, so enough with the memes. Let's proceed with the last one, which is the Newton's third law of motion. That is the law of interaction, and this one's my favorite because according to this law, if two objects interact, the force F12 exerted by object 1 on object 2 is equal to, in magnitude and opposite in direction, to the force F21 exerted by object 2 on object 1. Or mathematically, that's F12 is equal to negative F21. So let's say, for instance, we have here the one that we have before, the man pushing the pole. Alright, so if this is the pole, so the pole is considered as the object 2, the man is considered as the object 1. So since the man is pushing the pole, so the man is definitely exerting a force, which we now call as F12, because this is the force exerted by object 1 to object 2. And since the pole is not moving, so the force is now getting is similar in magnitude with F12, and this is opposite in direction of F12. That's why we have your negative sign. That's negative F21. This is the force exerted by object 2 on object 1. That's why the pole isn't moving, because it's similar in magnitude. They are equal but opposite in direction. So in order for the man to actually move the pole, the man needs to exert greater amount of force towards the pole, or vice versa. So if the pole can actually move the man, or if the pole wanted to move the man, then the pole should exert a greater force or greater magnitude of force towards the man. Alright, but it's quite impossible to do that. Alright, next, aside from this, a great example would be on a chair. So the chair is exerting a force upward, which is the normal force, right? And it's to support the weight of the of a certain object that would be located on the chair. So let's say a person with a greater weight is seated on this chair. So let's say the weight of the person is equal to 155 newtons. Negative 155 newtons, because it's located downwards. Normal force exerted by the chair towards the person is equal to 100 newtons. So since they're unequal in magnitude and opposite in direction, what happens to the chair? The chair will eventually break because it cannot actually support the whole the weight of the whole system. Alright, so it will eventually break. Or in bridges, at the end of the bridge, you will see there the maximum weight limit for the vehicles that could be on the bridge, because let's say the maximum weight limit of the bridge is 10 tons, and the cars located on the bridge exceeds 10 tons, then the bridge would eventually crumble down, or will be break, or will be broken into two. All right. So another examples, other examples of Newton's third law on daily basis would be this. So a cat. So this cat is rowing the paddle, is rowing a boat using a paddle, and then the paddle is moving backwards, but the motion of the boat is moving forwards. All right, so that's an example of Newton's third law. Aside from that, the rocket. So the chemicals spewed by the rocket is downwards, but the movement of the rocket will be upwards. Aside from that, this bird. So the bird or the dove is the dove's wings. So as the dove's wings move downward, the air beneath it is pushed downward as well, and the movement of the dove is upwards, and vice versa. So if the wings of this bird is pushed upwards, then the air is also pushed upwards, then the movement of the bird will be downwards. And lastly, this one. So if a person actually slaps you in the face with a force of 50 newtons, let's say, the applied force is 50 newtons. So even if you don't take it back to the person, your face actually does the work. So your face exerted equal amount of force to the hand, or to the palm of the person. So your face exerted 50 newtons of force to the palm of that person. So even if that person doesn't admit it, that he's in pain, or he's in pain because of the of the slap. So because of Newton's third law, you already got your revenge. So that would be all. And on the next video, we will be discussing analysis of laws of motion. So that's more of problem sets in the applications of Newton's laws of motion. So hope to see you there. Thank you.